Hello all, I'm Yogesh Singh. Welcome to my YouTube channel, Yogi's Data Lab. So today we are going to talk about a case study of classification problem where we will look into the defaulters who are going to default and who are not going to default. Since it is a yes and a no problem statement, hence we will do a classification problem statement. This we are going to solve using the algorithm logistic regression. Now let us start with the case study. So here you can see on the screen that we have to figure out which customer is most likely to default. The data that you have been given is the customer ID, status checking account, duration in months, credit history, purpose credit taken, the credit amount, savings account, years at the present employment, interest rate on income, marital status gender, other debtors, guarantors, current address years, property, age, other installment plans, housing type, number of credit cards, job, dependents, telephone, means the type of phone number provided, foreign worker, and default on payment. Now, this is a target variable. So we'll start working towards this. So we'll start importing the libraries where you see that we have used the train test split, we are using logistic regression, we are using sklearn matrix for all the matrix that we are going to use like recall, precision, F1. And now I'll read my data set. After reading the data file, I'll look at the head and it shows that I have my customer ID, I have my other columns. The data seems to be pretty clean. The column names are clean. And my target variable, which is the default on payment, which is in zeros and ones. I'll check the shape. It shows me I have 5,000 rows and I have 22 columns. These are my column names, which I have seen, and they seem to be pretty clean. I don't need to clean them. I'll drop customer ID because ID is something which is not going to contribute towards my target variable, based on which any specific customer ID is not going to contribute whether the person is going to uh, default on payment or the person is not going to default on payment. So I'm going to drop the customer ID. I'll correct my spelling of purpose credit taken. It seems to be wrong, so I'm correcting this. I'll replace any spaces if in the column names with no space. And this is the final data which I'm getting. When I look at the info, it shows me that I have no missing values. I have 8 integer and 13 object columns. Number of unique values when I'm looking at, I don't see any zero variance column, which is good. Number of missing values, I don't see any missing values. When you look at the description, what does it show you? It shows you on an average, the credit amount that is taken is 3,271, which is more than the median, which is 2,319, which means that the data is skewed towards the right. The duration is also slightly skewed towards the right because the mean is greater than the median. Interest rate is approximately same, so which is fine. Current address years is also approximately same. Age is very slightly skewed towards the right with a minimum of 19 years and a maximum of 75 years. Number of credit cards, on an average, people have one credit card ranging from 1 to 4. Dependents, one dependent with a minimum of one dependent and a maximum of two dependents. Then when I look at the default on payment, I have around 29.9% of ones and the remaining are zeros. So I have plenty of ones in my data. Then you will look at the categorical values. So you see that there are all the values are encrypted over here. They are masked with different values, so we won't understand much over here, so you can't do much about this. Now I'll go ahead and look at the histograms. So a couple of them seem to be skewed, like default on payment, current address in years is skewed slightly towards the left, age is skewed towards the right, duration in months is skewed towards the right, credit amount is skewed towards the right, but we'll leave them as it is for now. Let us build a model and see how the results are. I did not do the EDA here in detail because I didn't want to make the video lengthy. You can go ahead and certainly do the EDA for your using a univariate, bivariate and multivariate for all your numerical columns and categorical columns, and try to understand the pattern. Here I'm just replicating or trying to show you how logistic regression works. So I didn't do much into the EDA part over here. So here I am converting the objects into categories, which you can see has been converted here. The reason why we convert object into category is the data size becomes manageable. It becomes a bit smaller, and the processing becomes a bit faster when you're handling it in category rather than using an object. So this was a basic part which we do in every machine learning problem. Now let us concentrate more on the model building. So when I look at the model building, what I've done is I have dropped my default on payment, which is my target variable, and I've created my independent data set. And I have created my dependent data set, which is Y, which is the default on payment. Now, for the independent data set, I am creating my dummies. And using these dummies, I am going to go ahead and create my train and test data set. So I'm doing a train test split. 70% goes into train and 30% goes into test. I'm using a random state of 5, means I'm setting a seed of 5 over here. Now, I'm creating an object of logistic regression and I am fitting it on the train set. And this is what is I have to do for logistic regression. My model is done. Once this model is built, once I have done my logistic regression over here, I'll use a default threshold or a default cutoff of 0.5. If you remember the sigmoid function, in the sigmoid function, we have values at 0, we have values at 1, and we are going with the threshold of 0.5. Means anything greater than equal to 0.5 becomes a 1, anything less than that becomes a 0. So I am doing a logreg.predict. Logreg is your model name over here. And since the model is already ready, I am doing a dot predict on the train set. Similar to what we did before in linear regression, I am predicting on the train set from which I learn to see exactly how the results are. So if I do logreg.predict on the train set, I have got my predicted values in pred train. Now I'll create a confusion matrix. Now what was a confusion matrix? A confusion matrix is nothing but a cross table between the actual and the predicted values. So I am giving a confusion matrix with my actual values, which is y train, and pred train, which is my predicted values. So you can write it in a way. Let me write it. So you'll get it something similar to this as actual, and you'll have zeros and ones, and it is you have predicted, and you have 0, and you have 1. Now these values that you're seeing here, this 2240, this 2240 is coming here. This is, let me write it here, 2240. Then you have 237 over here. So you can say this is here. Then for ones, you have 575 here, and you have 448 here. So what it means is, whenever your actuals were zeros and you predicted it to be zeros, these are the count, means these are the count of true negatives. When you talk about this, this is actually 0 and predicted 1. So these are the count of false positives. These are actual ones and predicted zeros. So these are the count of false negatives. An actual 1 and predicted 1. So these are the count of true positives. So this that you see over here is giving you that matrix of the actual being predicted as actual 0 being predicted as 0 means true negatives. Actual 0 being predicted as 1 means false positives. Actual 1 being predicted as 0 means false negative, and actual 1 being predicted as 1, which is true positive. So, well, this is what I got in the confusion matrix. Now I'll do it on the test set. So on the test set, I am getting similar, these many true negatives, these many false positives, these many false negatives, and these many true positives. Now, since I've got my confusion matrix, I have built a model, I have predicted on my train set, on my test set, I will go ahead and compare the accuracy, recall, precision, and F1. So there are commands which you can use like accuracy score for getting your accuracy, recall score for getting your recall, precision score for getting your precision, and F1 score for getting your F1. You need to give the inputs as your actual value and the predicted value. So here I am giving the actual value of train and the predicted value of train. Here I am giving the actual value of test and the predicted value of test. Similarly, I'll do it for recall, precision, and F1. I have given the similar results. And if you look at this, I was concentrating on the recall here, trying to identify how many defaulters am I able to predict? And I see that the results are pretty poor, 43 or 44% on an average, approximately rounded off. We can say that the recall on the train set is 44% and the recall on the test set is 43. The model is not overfitting because the difference between the train and test is within 2%, but the recall value is very low. This is something which is not really good and I need to improve on this. So let us go ahead, let us try to see more things. So I'll go ahead and plot a ROC AUC curve, your receiver operator characteristics. So here I am doing it on the test set. I give my Y test and I'm using log reg dot predict proba. When you do predict proba at this point, what it does is it predicts the probability. So see here what we did in this case. When I did predict, it was by default taking a threshold of 0.5. I don't want 0.5. I want the probabilities here, right? So what I'll do is I'll, instead of using predict, I'll use predict underscore proba. So when I'm using predict underscore proba, what it is doing is it is predicting me the probability on the test set. But when it does so, what it will do is it will also, when you use this and you print this somewhere just prior to this code, you'll see you'll have a column 0 and a column 1. Column 0 means the probability of the occurrence of 0 and column 1 means the probability of occurrence of 1. Now there are only two things that can happen. A 0 can happen and a 1 can happen. So the probability of the occurrence of 0 is 0.90. The probability of occurrence of 1 will become 0.10, means 1 minus 0.90 is 0.10. I want the probability of the occurrence of 1s, and that is why you'll see I have taken 1 over here. This represents all the rows and this is the column 1. Now this will give me the ROC AUC. I am looking at the ROC curve. Similarly, I am giving my values over here, and this is all that I need to change in this code. Rest everything is pretty standard. And when you look at this, this is what you will see. You will see this is your ROC curve, how it looks like. And the area under the curve comes out to be 80%. So generally we go with an area under the curve as 70%. Here we are getting 80%, which means I'm doing a decent job. Despite that, I know that my recall is really not that good. So what can I do now? So what I'll do is I'll go for optimal cutoff or optimal threshold. So as we discussed in the theory part, there were a couple of methods where out of which we discussed the distance method, distance cutoff. We talked about KS cutoff or Kolmogorov-Smirnov cutoff. We also talked about REPR cutoff or the F1 cutoff. So we are going to use these now and try to see how it impacts my results. So here, when you look at this, I am predicting the probability on the train set. So this is how it will look. It means for the first record, the probability that it is going to be a 1 or the output is going to be a 1 is 0.4559. For the second record, the probability that the output is going to be a 1 is 0.4264. For the last record, the probability that it is going to be a 1 is 0.9275. So this is what is the probability that is being predicted for my train set. Now I'll create a cutoff matrix. I have to use these values to come up with the optimal threshold. So what I'm doing is I'm creating a data frame eventually where I'll have these column names: cutoff probability, true positives, false negatives, true negatives, false positives, actual number of positives, and actual number of negatives. So I'm creating a data frame with this column names, and I'm creating a range from 0 to 1.00 with a gap of 0.01. Since I'm using a range, hence I have given it 1.01 so that it creates the values up to 1.00. Now, the concept here is whenever my cutoff probability, this thing, I'll compare the actual predicted probability, which I got here, this one, with the cutoff probability. And if it is greater than the cutoff probability, like the case where we were taking 0.5 and anything greater than 0.5 was 1, anything below was 0. Similarly, let's say I assume that my cutoff probability eventually in a loop is coming to be 0.2. So anything greater than 0.2 will be 1 and anything greater than 0.2 will be sorry, anything smaller than 0.2 will be 0. Similarly, at certain point, it will move on, the loop will move on, it will come to 0.70. Anything greater than 0.7 will become 1, and anything less than 0.7 will become 0. So what I'm doing is I am moving the cutoff probability from a scale of 0 to a scale of 1. 0, 0.01, 0.02, 0.03, and at every point, I am saying that assume this to be a cutoff. Now, anything greater than these points, whatever I'm assuming, becomes a 1, otherwise it becomes a 0. And whenever my ones and zeros keep on changing, my true positives, false negatives, true negatives, and false negatives will also change. Now, since my TP, FN, TN, and FP are also changing, my recall, my precision, my F1, everything changes. And this is what I'm trying to achieve here. So here in a loop, when the cutoff is 0.00, if my predicted probability is greater than 0.00, convert that into, this will be a true and a false, convert that into an integer. So whenever my predicted value is a 1 and my actual is a 1, sum up all such values and put it in true positive. Similarly, when the predicted is 0 and the actual is 1, it means it is a false negative. Sum up all such values and put it in false negative. Likewise, you'll get your true negative and false positive. P, which is the actual number of positives, is equal to the number of true positives plus number of false negatives. N, which is the actual number of negatives, is equal to the number of true negatives plus number of false positives. Now I am going to use all these values that are calculated. Let us say the beginning is 0.00. So at 0.00, what is the value of TP, FN, TN, FP, P, and N? This loop will go now and become 0.01 because you see here we are increasing this by 0.01. Now at 0.01, what is the TP, FN, TN, FP, P, and N? At 0.02, what is the TP, FN, TN, FP, P, and N? And this will keep on repeating till 1.00, where I'll find out the TP, FN, TN, FP, P, and N. So this will eventually give me a matrix, something like this. So I've taken a head of the cutoff matrix that we have developed and see at cutoff probability 0, 0, because every probability is going to be greater than 0. So everything will be marked as a 1. When everything will be marked as a 1, it means the actual zeros have been marked as 1s and actual 1s have also been marked as 1. So at a cutoff probability of 0.00, you will only get true positives and false positives. So this is what you see, you get only true positives and you only get false positives. At 0.01, you'll get different values, and eventually you see that your true negatives have started increasing. Now, since I have built this matrix, I can now calculate the value of sensitivity, specificity, distance, KS, recall, precision, true positive rate, false positive rate, and my F1. So all of are these matrix which we covered in the theory part, and this is what I am putting it here. Based on this, you'll see that you have got all your matrix over here. Now, if I have to select any cutoff, when we talk about distance cutoff, talk about that whenever the distance is minimum, the corresponding probability is my distance cutoff. Whenever my KS is maximum, then the corresponding probability is my KS cutoff. Whenever my F1 is maximum, the corresponding probability is my F1 cutoff or REPR cutoff. So here I'm doing the same thing, picking up the minimum distance, picking up the maximum KS, you see here maximum KS or the maximum F1. When you look at the probabilities now, you see that your distance threshold comes out to be 0.23. Your KS threshold comes out to be 0.21 and F1 comes out to be 0.21. Now I've saved these three, the distance cutoff, KS cutoff, and F1 cutoff in a list over here. And I am predicting on my train and test whenever it is greater than the cutoff. Means whenever first time greater than distance cutoff, second time greater than KS cutoff, and third time greater than F1 cutoff. and I'll calculate the accuracy, recall, precision, and F1. So you can see here that whenever I'm using distance cutoff, my recall is coming out to be 0.82 on train and 0.81 on test. Now you can see here the importance of a cutoff. At a base threshold of 0.5, we were seeing it was giving me a result of 43 and 42, if I remember it correctly. But the moment I used the distance threshold, my recall shifted from 43% directly to 82%. So it's a huge, huge jump just by shifting the threshold and not rebuilding the model. The model is already built. I'm just shifting the threshold. I'm shifting the probability with which I can get these results. So when you look into this, here with the recall, I am getting 0.82 and 0.81. When I'm using your KS threshold or your F1 threshold, because both of them had the same value this time, I see the recall on train is approximately 85% and that on test is 86% approximately. So it is even much better, and they are not overfit either. They are within a gap of 2%. So I am doing a decent model in terms of recall. So this was the importance of selecting a threshold. Now, we talked about the threshold. We said that we are not going to talk about accuracy. Remember, we discussed why accuracy is not the best measure. So we are concentrating on the recall in this case. The last concept that we covered was concordance. Now, in concordance, this is a function I've created. You can use this, which is to calculate the concordance, where we said that it will pair with a 0 will pair with a 1, and then it will compare whether the probability of 1 is greater than the probability of 0. So I am going ahead and passing the values over here for my data set. And what it does is, you see that it is showing you that the concordance percentage is 81.22. So as I told in the theory part, that we generally accept a model if the concordance is greater than 80%. So in nutshell, what you saw is, you saw that we built a Bayes logistic regression model with sklearn. We tried it with a threshold of 0.5, which gave me a very poor recall. Then we tried optimal threshold methods. We tried distance cutoff, we tried KS and F1, and we got the best results with KS threshold, which was 0.21. And the recall, which we were getting as 43 at 0.5, eventually increased to somewhere around 85, 86 with the KS threshold of 0.21. Then we also looked at the ROC curve, AUC curve, where we saw that we are getting the area under the curve as 80%. So it's a decent model. Along with that, we also saw that the concordance percentage is 81% over here. And hence, all these indicators do show me that I have a decent model and I can go ahead with this model. So this is all we have for the case study. So if you did enjoy this video, you did learn something more from this video, please do like, share, and subscribe, and see you in the next video. Thank you, everyone.